All right, so we've covered forming ionic bonds, the different types of ions that go into them. Let's talk about some properties. If you recall, ionic bonds involve the transfer of electrons. That's why you always have that positive ion and negative ion. The positive ion gives up its electron and gives it to the negative ion. So this electrostatic, positive versus negative attraction is what forms the bond. And that makes these bonds very difficult to break. All right, so the ionic bonds are considered very strong. All right, the chemicals themselves have strong, solid structures, and they require a lot of energy to break them apart, to melt these substances, and even more energy to evaporate them into gases. So, quick review here. What kinds of atoms make positive ions versus what kinds of atoms make negative ions? And a hint you may want is think in terms of metals versus nonmetals. But metals, need my pen ready here. Metals make positive ions and nonmetals make negative ones. All right. So that leads to another property of ionic bonds. Nearly all of them are a metal plus a nonmetal. The only exception to this is, if you recall, those polyatomic ions, which are all nonmetals. You can run into some rare examples that are formed completely from polyatomic ions that don't have a metal in it, but that's pretty rare. So, talking in a little bit more detail about this organized, hard structure. So this is sodium chloride, but this would apply to any salt, any ionic compound. All right, so if you remember, the term salt applies to all ionic compounds, but they all form this crystal lattice structure where you have your alternating positive and negative ions. What this does is it actually leads to some attraction between the neighboring ionic compound. All right, so like this sodium chloride has a slight attraction to this sodium chloride because you've got your, negative, that's going to be your positive ion. This is going to be your negative ion. All right, and then same thing. This one has a slight attraction. All right, this one has a slight attraction. So you've got all this alternating positive and negative, which not only makes a strong electrostatic attraction within the singular compound, but it also attracts the neighboring ones. All right, and all ionic compounds can form these crystal lattice structures. So, because of that, the bond itself is super, super, super strong. But the attraction between the neighboring compounds isn't all that strong. So your ionic compounds, when you have lots of the molecules near each other, they're actually quite brittle, all right? So if you've ever taken a chunk of salt and, tried smashing it against a table or something, it falls apart pretty easily. All right, you're not breaking bonds doing that. All you're doing is separating neighboring ionic compounds. All right, so you can see, these, if you look at the breaks, they're all kind of very like straight line breaks. All right, and that's because you're just taking that crystal lattice and you're breaking off this chunk here. All right, you're just taking a group of slightly attracted neighboring ionic compounds and breaking them into two groups instead of just one. All right, so they're very brittle. They break apart pretty easily. Just note that all you're doing is breaking apart neighboring compounds, not the actual bond. All right, there's also the ability of ionic compounds to dissolve in water. All right, when you add salt to water, it dissolves. All right, what that means is, and again, this isn't actually breaking the bond, all right? It's more the water is interfering with the ability of these two to kind of interacting with the attraction there. All right? So you will have your negative ion and your positive ion. They're still ions. They're still have transferred their electrons, but you kind of make the electrical charge related to that more readily available. All right? So not only does it dissolve well in water, because if you recall from biology, water has a partial negative charge and then a partial positive charge with the hydrogens. That partial charge interacts well with the ions. Right? So that leads to the ability of nearly all ionic compounds to dissolve really well in water, but that also releases the conductivity ability of ionic compounds. Right? Because you have now the separated positive and negative charges, which will allow electrons to flow and electricity to conduct. So, a just general list of properties you want to be familiar with. As far as the structure of an ionic compound goes, they form crystalline solids. They always have a metal and a nonmetal. Rare exception to that, but it's pretty much always a metal and a nonmetal. And they're brittle. All right, melting and boiling points are really, really high. All right, because it takes a lot of energy to break these things down. Their conductivity is great, but those ions do need to have some form of separation. So you either have to have it dissolved in water, which is what aqueous means, or melted, so that those electrons can flow freely. And they're soluble in water. So this is definitely the slide to write down some notes on. And here's an example of something you can use those notes on. Right? Which of the following would have the lowest boiling point? All right, so first thing first here is our ionic compounds. Do they have high boiling points or low boiling points? All right, ionic has a high boiling point. So what we're really looking for is something that is not an ionic compound. All right. Now, a couple of different ways you can go about this. We haven't covered the other types of compounds yet. So, like, we haven't covered covalent bonding. But there's also, you can think about the fact that structurally, an ionic compound always needs to have a metal and a nonmetal. So, if you go to your periodic table and you look up potassium, which is K, and chlorine, sodium and oxygen, calcium and nitrogen, because glucose, I'm not sure if you remember the formula for that, but if you did, you might remember it being C6H12O6. All right, but even if you couldn't remember that, all right, so pretend we don't remember what that is. If you go to your periodic table, and I'm sorry, calcium nitride, you can see that these three are all metals. These three are all nonmetals. So by process of elimination, those are all ionic compounds. Glucose, which is C6H12O6, which are all nonmetals, has to be your non-ionic compound. So this is a way that you can use this information to answer questions. All right, so really it's the root of the question. You're going to, based on that, decide, okay, does this match properties of ionic compounds or does this match properties of something else? And then, that way you know what you're looking for in the problem. All right, because likewise, if this had the root saying which of the following would have the highest boiling point, all right, you'd have to have different choices, but there would probably be one that was an ionic compound and three that were something else.